So if I consider that this is the direction in which the asteroid was moving initially, when the dart collide, like this is the direction in which the dart collide, this will cause the direction of asteroid to change. Like this is a new direction of asteroid and the dart together. What we need how much the angle is changed from the original one. So if I consider, because if this was 0.16, this will be equals to 0.16 as well in terms of making a triangle. The initial one, it's the same thing. We need this angle. And so we already know, according, like in the part A, they already mentioned that the change in the velocity for an asteroid is 0.4 millimeter or 0.0004 meter per second. That change in the velocity is given. So we need this angle theta. So with reference to this angle theta, what we have this is a base and we have perpendicular. So we can use tangent theta. Tangent theta is equals to perpendicular divided by base. So tangent theta is perpendicular, which is 0.0004 divided by base, which is 0.16. And theta is equals to tan inverse the answer. So you will get approximately 0.14 degree. There will be a change in the angle. Is it clear, this part B? Is it clear or should I repeat? Working of part A using a conservation of momentum is substituting the values. Yeah, sure. I will solve part A as well by substituting the value for a conservation of a momentum. If we solve for a first part, if we use a conservation of momentum, according to conservation of momentum, the total momentum before collision is equals to total momentum after collision. So asteroid is there on a collision course and it can be deflected by moving, making a fast moving craft collide with it, which is still very far. And to test this idea, the spacecraft dart to collide with a small asteroid. And after the collision, the dart and the asteroid will stick together. So it means they will have the same speed. The dart have a relative speed of 6,250 and it collide with an asteroid that is expected to cause a change in the asteroid velocity by 0.4 millimeter per second. So change in velocity is given. And show that the mass of asteroid is about 5 exponent 9. So according to conservation of momentum, the total momentum before collision is equals to total momentum after collision. And in this question, because the change in the velocity is very small, so change in velocity is actually equals to like 0.4 millimeter per second, which is a very small value. So it is like you can consider that the change in the velocity for the dart is also very small. Like it will more or less it's same. On that basis, like they use the formula m1u1 plus m2u2 is equals to m1v1 plus m2 v2. If I move like m1u1 plus m1v1 is equals to m2v2 minus m2u2. Now, how it is done? Like, because from the values you can clearly see that the change in velocity for the asteroid is very small, so change in velocity for like change in velocity will be approximately equals to the initial velocity of a dart. That's why when we take a common m1, we take a common. This will move. This is supposed to be negative, so it will be u1 minus v1. And this in the question. So we consider here u1 minus v1 is approximately equals to u1. On that basis, they calculated because in the question, the change in the velocity of asteroid is very small. So change in velocity of dart should also be very small. That's why this u1 and u1 minus v1 is approximately equals to u1. And here we take m2 common, so it is v2 minus u2. So when we substitute here m1 in place of u1 minus v1, it's like u1 only because the change is very small. And it is m2 v2 minus u2. So we have m1 which is 300. We have u1 which was 6,250. We have to find m2 and the change in the velocity is given here. So we just divide, we get the value for m2. Is it clear? Because the change in the velocity was very small, so they consider that v1 u1 minus v1 is approximately equals to u1. Then next out, this was question 23. And the last 24, then 26. Okay. Question 24, in a game of air hockey, a small identical disc move across a frictionless surface. One disc with a velocity of 0.6 collide with a stationary after the collision. So the angle is total angle is 90. So this shows that the collision should be elastic. Calculate the velocity v1. So whenever two objects are colliding with each other and they changes the direction after collision, so you can take a component of the momentum, either horizontal or vertical. So if I take horizontal, the mass of a disk is not given, but I guess it will cancel out as it is common. So in x direction, when I take conservation and momentum in x direction, so this mass is m into 6.9 plus this one is 0. And the horizontal component for this one will be m cosine like mv because mass into velocity. So m into 6 cosine 30 plus the mass of a disk is also m here because they are identical. So mass will be m and the momentum will be velocity will be v and it will be cosine 60. So m is common, m will cancel out. So m is common, this totally cancel out. Then we are left with this is 6.9 is equals to 6 cosine 30 plus v cosine 60. Then you just have to solve. You just have to solve like substituting a value. Like this will be 6.9 minus 6 cosine 30 divided by cosine 60. This will give us a value for speed, which is about 3.4 meter per second. Explain whether the collision is elastic or inelastic. So you have to calculate after getting for speed, like for a kinetic energy, we don't bother about the angle. We calculate the kinetic energy before, which is equals to half mv square. And that must be equals to kinetic energy after. So we just substitute the value here, like it will be half m, we don't know. Speed is 6.9 and then square is there. So when we simplify m, it will we get the answer in terms of m, so it will be equals to 24m. That's the kinetic energy before. Kinetic energy after. So speed is 6, and this speed we calculated in the previous part, which was 3.4. So we'll find half mv square for this one, like half mv square for this one, and half mv square for this other one. And we add to get the total. We don't bother about angle, and we get the total kinetic energy after the collision, which is about 24 m joules, and it is also 24 m joule. So the kinetic energy before and after is equal. It means this momentum is conserved. Then the last doubt, question 26. A student investigated the elastic collision using an air track. Air track has shown the friction between the glider and air track was negligible. The glider of mass 0.5 moved towards a glider B at a speed of 0.6, which is initially at rest. The glider collide with the velocity VA. The glider collide and the velocity VA of a glider after collision is measured. The process was carried out by using various mass of a glider B. Initial speed of a glider A was kept same. Use a result shown from the graph. Say B is the doubt. Calculate the velocity VB of a glider after collision when the mass is 1.4 kilogram. Do not assume that collision is elastic. So you cannot say the kinetic energy is conserved, but you can consider momentum is conserved. When the mass of a B is 1.4. So mass is equals to 1.4 is there. And we need velocity of a B after collision. Okay. Assume that the collision is elastic. Do not assume that the collision is elastic. So use a conservation of a momentum m1 u1 plus m2 u2 is equals to m1 v1, because it is in one dimension, so we can use this formula m2 v2. So mass of the first one for A, that is 0.5 is there in the question, and the speed is 0.6. So this is 0.5 into 0.6 plus the mass of a second one we don't know, mv we don't know, and initially it was at rest. Sorry, the mass is 1.4, because in the question they asked calculate the speed when the mass is 1.4. So 1.4, but the initial speed is 0. M2, M1 U V1. So that is equals to 0.5. And then we'll find the speed from the graph. When the mass of B is 1.4, so 10 boxes equals to 0.5, each is 0.05. So this will be 1.1, 1.2, 1.3, 1.4. So 1.4, 0.29, I guess. Yeah, but negative 0.29. Negative. So we'll substitute as negative minus 0.29 plus M2 is 1.4 and V2 we don't know. So we just simplify, like we have this value, we just simplify and find the final speed of this mass B. Like you just have to solve for that. And then determine whether the collisions are elastic or inelastic. You have to use a formula. The kinetic energy before and after must be equal. I like half mv square before collision should be equals to half mv square for mass A and for mass B. Their sum of the kinetic energy after collision must be equals to uh, before collision for a collision to be elastic. So this was question 26. Any other question or doubt from this exercise?